So, hello friends. So, welcome to lecture series on non-linear programming. So, in the last lecture we have seen what separable programming problems are. I told you that if the objective function as well as all constraints are separable, then we say that the problem is the separable programming problem. Also, we have seen in the last class that if a function of one variable is given to you, how we can find out the linear approximation of that function. Now, let us see how to solve those problems. Okay. So, what is our solution procedure? Let us see. So, this problem giving maximizing f(x) is equals to 3x1 square plus 2x2 square subject to x1 square plus x2 square less than equals to 9, x1 plus x2 less than equals to 3 and x1 x2 non-negative is a separable programming problem, because we can quickly see that the objective function can be separated into two functions and each is a function of one variable only. The first constraint is also separable and second constraint is also separable, and non-negativity condition is also separable. So, it is a separable programming problem. Okay. Now, how to solve this problem? So, let us see. So, what is the problem? It is maximizing f(x) equals to 3x1 square plus 2x2 square subject to it is x1 square plus x2 square less than equals to 9, x1 plus x2 less than equals to 3 and x1 greater than equals to 0 and x2 greater than equals to 0. Okay. Now, the objective function can be rewritten as f1 x1 plus f2 x2. This constraint can be rewritten as g1 x1 plus g2 x2 less than equals to 9. This constraint can be rewritten as h1 x1 plus h2 x2 less than equals to 3, and non-negativity condition you can remain it as it is. You can leave it as it is. So, what is f1 x1? f1 x1 is 3x1 square, as you can simply see, function of x1, and f2 x2 is 2x2 square. If you see g1 x1, g1 x1 is x1 square, g2 x2 is x2 square, h1 x1 is x1 and h2 x2 is x2. Okay. So, this is because the problem is separable programming problem. Now, to solve this problem, first of all you find the bounds of the variables. How many variables are involved in this problem? x1 and x2. First find bounds of the problem. So, you can simply see, you can easily see that minimum value of x1 is 0, okay, and from this constraint maximum value of x1 which it can attain is 3, and if you substitute this over here, so it is 3 square means 9 and 9 is less than equal to 9, that is true. So, we can simply say that the bounds of x1 is 0 to 3. Similarly, if you see the lower bound of x2 is 0, it is clear, and the upper bound from this constraint we can say it is 3, which also satisfies this constraint. So, the x2, the bound for x2 will be less than equals to 3 greater than equals to 0. So, first of all you find bounds corresponding to all the variables involved in the problem. Here we have only two variable x1 and x2. So, find bounds of corresponding to all the variables. Next is, now once finding the bounds we will find, now now it is function of x1, it is function of x1, it is function of x1. Okay. Now, we will see x1 is between 0 and 3, variable x1, okay, is between 0 and 3. So, we can mark grid points as 0, 1, 2, 3. These are the grid points. This is A naught, A1, A2, A3. Okay, this is A naught, this is A1, this is A2, this is A3. So what is F1 X1 at these grid points? What is F1 X1? It's 3x1 square. What is F1 X1 when A naught is 0? So you substitute 0 here, it is 0. You substitute 1 here, it is 3. You substitute 2 here, it is 4 into 3, it is 12, and then it is 27. Okay. Now you focus on G1 X1. G1 X1 is X1 square. At A naught equal to 0, this is 0. So it is 0. When you substitute A1 equal to 1, basically we are finding the value of F1, G1 and H1 at these grid points. When A1 is 1, it is 1. When A2 is 2, it is 4. When A3 is 3, it is 9. And H1 X1, it is X1, so it is 0, 1, 2, 3. Okay. This is corresponding to variable X1. Now for X2, the bound of X1 X2 both are same as we have already seen. So again we will divide this in between 0 and 3. We can mark grid point as 0, 1, 2, 3. Okay. This is only for convenience. We have make this as a grid points 0, 1, 2, 3. Now again this is A naught. Suppose it is A1, it is A2, and it is A3. Now it is F2 X2. Now at A naught equal to 0, F2 X2 is 0, and at A1 equal to 1, it is 2 into 1 is 2. At A2 equal to 2, it is 8, and it is 18. 9 into 2 is 18. Now it is G2 X2. G2 X2 is X1 square, X2 square. At 0, it is 0, 1, 4, 9. And at it is H2 X2, which is X2. So it is 0, 1, 2, 3. So we first find the bounds corresponding to all the variables involved in the problem, then fix up the grid points corresponding to all the variables, find the value of F1 X1, G1 X1, H1 X1 and so on. Okay. Similarly for the second variable and so on. Okay. Now we will write the linear approximation of this problem. How to write? Now the objective function will be maximizing fx is equals to. Now suppose corresponding to this grid point we have lambda naught, lambda 1, lambda 2 and lambda 3, and corresponding to variable x2 we are mu naught, we are having mu naught, mu 1, mu 2, mu 3. Okay. As we have already seen. Okay. So how to write fx? Fx is nothing but f1 x1 plus f2 x2. We first find the linear approximation of f1 x1. Okay. The linear approximation of f1 x1 is 0 into lambda naught, 3 into lambda 1, 12 into lambda 2, 27 into lambda 3 plus f2 x2. How to find the approximation of f2 x2? That is 0 into mu naught, 2 into mu 1, 8 into mu 2, 18 into mu 3. So what will be fx? Fx is nothing but the sum of linear approximation of f1 x1 and f2 x2. So it will be 0 into lambda naught plus 3 into lambda 1 plus 12 into lambda 2 plus 27 into lambda 3 plus 0 into mu naught plus 2 into mu 1 plus 8 into mu 3 mu 2 plus 18 into mu 3. Subject to what are the conditions? The first condition involved, the first constraint involved the sum of G1 x1 and G2 x2. Okay. So, what is the linear approximation of G1 x1? It is 0 into lambda naught, 1 into lambda 1, 4 into lambda 2, 9 into lambda 3. Okay. That is lambda naught f a naught, I mean G1 a naught plus lambda 1 G1 a1 plus lambda 2 G1 a2 plus lambda 3 G1 a3. So, it is 0 lambda naught plus 1 lambda 1 plus 4 lambda 2 plus 9 lambda 3 plus corresponding to G2 x2, it is 0 mu naught plus 1 mu 1 plus 4 mu 2 and 9 mu 3, and it is given to us it is less than equals to 9. It is given to us in the problem that x1 square plus x2 square is less than equal to 9. So, it is this is the linear approximation of x1 square and this is the linear approximation of x2 square, and a sum must be less than equal to 9. Now, x1 plus x2 less than equal to 3, the second constraint. So, what is the linear approximation of x1? It is 0 into lambda naught plus lambda 1 plus 2 lambda 2 plus 3 lambda 3 plus, and corresponding to S2 x2, it is again 0 into mu naught plus 1 into mu 1 plus 2 into mu 2 and less than equals to 3, and all variables all lambda i's and mu j's must be greater than equal to 0 for all I and j. All variables must be non-negative, okay, and of course lambda naught plus lambda 1 plus lambda 2 plus lambda 3 must be 1, okay, and mu naught plus mu 1 plus mu 2 plus mu 3 must be 1. Okay. Basically, what we are doing? First of all, we are seeing one variable x1. Forget about the other variables. We are making the linear approximation corresponding to that variable. Now, we are focusing on the second variable. Forget about the remaining variables, and we are making the linear approximation corresponding to those variables. So, these lambdas and these mu j's may not be same. So, we are making different constraint, lambda naught plus lambda 1 plus lambda 2 plus lambda 3 should be 1, and mu naught plus mu 1 plus mu 2 plus mu 3 should be 1. Okay. Now, at most the next condition, at most 2 lambda I is greater than 0 and they must be adjacent. Similarly, for lambda j's, for mu j's, they must be adjacent. Okay. The same condition is for mu j also. So, this will be the linear approximation of this problem, this non-linear programming problem. Okay. I mean separable programming problem. Now, the question arises how to solve this problem. Okay, we have find the linear approximation of the given function f, we have find the linear approximation of all the constraints, but how to solve this problem now? So, this problem is clearly a LPP, a linear programming problem. We can easily see it is a linear programming problem. Now, but we have another restriction, and restriction is at most 2 lambda j's, 2 lambda is a greater than 0 and they must be adjacent. They must be adjacent. Okay. And at most 2 mu j's are greater than 0 and they must be adjacent. This is the additional condition which we are having. Okay. So, how to take care of this condition while solving this LPP by simplex method? So, let us see. So, first it is less than equal to 9. So, we add a slack variable here S1 to make it an equation. Again it is less than equal to type, again we will add a slack variable S2 to make it an equation, and S1 S2 again must be non-negative. Okay. So, how to find x1 x2 in this problem? So, x1 x2 can easily find out. x1 will be nothing but it is 0 lambda naught plus 1 lambda 1 plus 2 lambda 2 plus 3 lambda 3. and x2 is nothing but 0 mu naught plus mu 1 plus 2 mu 2 plus 3 mu 3. Now, let us see how to solve this problem. So, this is all we have discussed. Okay. So, this is simply a notation lambda 1, lambda 2, lambda 3, lambda 4. I here have taken lambda naught, lambda 1, lambda 2, lambda 3. So, it is not a problem. These are simply notations. Okay. Now, how to solve this problem? Let us see. So, first we will make the first table of the simplex, first simplex table. We have seen that this is the LPP. Okay. What is the here it is lambda 1 and here we are having lambda naught. Okay. So, so how to solve now? So, we write all the variables here. The variables which are making identity in the first table are S1, S2, lambda 1 and mu 1. These are making identity in the first table, as we can easily see. So, the basic variable in the first tables are S1, S2, lambda 1 and mu 1. Okay. These are the basic variable in the first table, S1, S2, lambda 1, mu 1. Okay. Now, the coefficient of lambda 1 here is 0, 0, 1, 0. So, it is 0, 0, 1, 0. Now, coefficient lambda 2 is 1, 1, 1, 1. So, it is 1, 1, 1, 0. Lambda 2 in the last constant is 0. Okay. So, similarly, we complete the table for lambda 3 it is 4, 2, 0, 0. So, it is 4, 2, 1, 0. So, it is 4, 2, 1, 0, we complete table. Now, the cost of S1 in the objective function is 0, 0 and lambda 1 is 0 and mu 1 is 0 in the objective function. In the objective function lambda 1 is 0, mu 1 is 0 and S1, S2 is not there. So, the cost is 0. So, how to find this negative of relative profits? As I already told you, this is 0 into 0 plus 0 into 0 plus 0 into 1 plus 0 into 0 minus 0 is 0. Okay. 0 into 1, 0 into 1, 0 into 1, 0 into 0, minus 3 it is minus 3. Similarly, we can complete the entire table. Now, as we already know, we will enter that variable which is having most negative value. Most negative means that is having most positive relative profit. Okay. This is minus 27 means the relative profit corresponding to lambda 4 is 27, which is maximum among all these values. So, this will enter. So, this variable will enter. Okay. We leave by minimum ratio. How to find minimum ratio? This is right hand side, 9 upon the entering column, 9 upon 9 is 1, 3 upon 3 is 1, 3 upon 3 is 1, 1 upon 1 is 1 and this is not possible. So, we leave it as it is. Now, we can now we are entering lambda 4. Okay. If we are entering lambda 4, if lambda 1 is leaving, then it is okay, we can enter lambda 4. If lambda 4 is entering, but lambda 1 is not leaving, then we can't enter lambda 4, because lambdas are must be adjacent. If lambda 4 is entering lambda 1, lambda 3 is not in the basis, lambda 1 is the basis and lambda 1 and lambda 4 are not adjacent. We are able to entering this variable only because lambda 1 is leaving. We have an option because all the ratios are same. So, we can leave any one and we are leaving lambda 1 because this is giving maximum relative profit. If instead of this we are leaving any other variable S1 or S2, then this entering is not possible, not allowed, because lambdas must be adjacent. Okay. So, we leave this, enter this. This is the pivot element. we make 0 here with the help of this minus 3 times this in the entire row, this minus 9 times this in the entire row, and this plus 27 times this in the entire row. We get the next table. Okay. Now, which is most negative entry? Minus 18. If we enter minus 18, if we enter minus 18 here, so it is mu 4 and mu 1 is already there on the basis. You can see if we enter this variable, the minimum ratio here is 0 upon 9, 0 upon 3, this is not defined, and 1 upon 1 is 1. So, we have to leave either this variable or this variable, either S1 or S2, and then mu 4 will come in the basis, and mu 4 and mu 1 are not adjacent. So, it is not possible. Okay. So, we can't enter mu 4. We can enter mu 4 only when mu 1 is leaving the basis, but mu 1 is not leaving because this ratio is not minimum, these two are minimum. So, we can't enter this. Next is you can enter the next negative, which is mu 3. If you enter this, so again 0 upon 4 is 0, 0 upon 2 is 0, and 1 upon 1 is 1. So, this is minimum. So, you will leave either S1 or S2. Okay. And if you leave S1 or S2, mu 3 is coming in the basis, and mu 3 and mu are not adjacent. So, again we can't enter mu 3. Okay. So, next is mu 2. If you enter mu 2 now, so if you enter mu 2, it is 0 upon 1 is 0, 0 upon 1 is 0, 1 upon 1 is 1. You have to leave one of the variable, say you leave S1. If mu 2 is entering, so mu 1 is adjacent to mu 2, it is allowed. Okay. Because we have an additional condition that if 2 lambdas, at most 2 lambdas are greater than 0, and they must be adjacent, and similarly for mu j's. So, this condition we have to take care of in the entire simplex algorithm. If this condition is violated, so that means our approximation, our linear approximation of this function is not possible. Okay. So, this is a pivot element, we complete the entire table again, making the identity corresponding to mu 2. Now, in this table we get all these entries, all capital Z, all these entries as positive. This means all relative profits are either negative or 0. So, this is an optimal table. Okay. And what is an optimal solution? Optimal solution is lambda 1 equal to 0, S2 equal to 0, lambda 4 equal to 1, and mu 1 equals to 1. And when you substitute in x1 and x2, x1 is this and x2 is this. When you substitute these values over here, so you will get x1 as 3 and x2 as 0. So, x1 equal to 3 and x2 equal to 0 are the optimal solutions, and value of the function is 27. Okay. So, you can see graphically also, if you see here, what is the first constraint? It is a circle, the region inside a circle with center 0 0 radius 3. Okay. So, this is this circle. This region, and x1 plus x2 less than or equal to 3. So, it is passing from these 2 points, and this is a feasible region. This region is inside the circle also, and x1 plus x2 less than or equal to 3 also, and x1 x2 non-negative. Okay. So, we are obtaining optimal solution at this point 3 comma 0 for this problem. Okay, x1 is 3, x2 is 0. So, in this way we can solve such type of problems. Now, suppose we have this problem, again this problem is separable. You can simply see, because the first function is x1, f1 x1 is x1, f2 x2 is x2 raised to power 4, G1 x1 is 3x1, G2 x2 is 2x2 square, which is less than or equal to 9. So, this problem is clearly a separable programming problem. Now, the important point to note here is, in the entire problem x1 is linear, in the entire problem x1 is linear. So, no need to make linear approximation of corresponding to x1, because in the entire problem, in the objective function as well as in all the constraint, the variable x1 is linear. So, no need to mark linear approximation of corresponding to x1. Corresponding to x2, we have to make linear approximation because it is non-linear corresponding to x2. How to make it? Again, first we will find the bounds corresponding to x1 and x2. Now, what is the constraint having? It is having only one constraint, that is 3x1 square plus 2x2 raised to power 4 or square less than or equal to 9. This is the constraint. Oh, 3x1, yeah. Now, x1 is greater than or equal to 0, it is given, and the maximum value which x1 can take is 3. 3 into 3 is 9, which is Holder's inequality, so x1 must be 3. Now, for x2, x2 must be greater than or equal to 0. Now, if you take x2 as 3, so it is 3 square, that is 9, 9 into 2 is 18, and 18 can't be less than or equal to 9. So, x2 can't be 3. Now, if you make it 2, so 4 into 2 is 8. So, that is the optimal bound for x2 is in between 2 and 3, which is in fraction, okay. 2 point something will be the upper bound for x2. Instead of taking that, we are making it strictly less than 3, okay. Now, corresponding to x2 only, we will mark the grid points and make the linear approximation, okay. Now, this is the grid points 0, 1, 2, 3, okay, because it is less than 3. Of course, 3 is not there in the domain of x2. So, the constraints will automatically take care of that thing, because when we are putting it less than or equal to 9, so constraint will automatically will not make mu1, mu2, mu3, mu4 such that it will exceed 9, okay. So, constraints will automatically take care of the feasibility of the problem. So, we can make f2 x2 as x2 raised to power 4 from the problem. Here it is x to power raised to power 4, and g2 x2 as 2 x2 square. So, we make all the functional values and the constraint values. We linearize the problem in the same way as we did earlier, okay. At most 2 muj's must be greater than 0 and they must be adjacent, same way. We form the simplex table using the same algorithm, okay. And now, here also you can easily see that if you enter mu 4 here, because it is most negative, if you enter mu 4, so by the minimum ratio it is 9 upon 18, that is 1 by 8, I mean 1 by 2, okay, and it is 1 by 1, that is 1. So, 1 by 2 it is minimum, so S1 will leave, not mu 1, and mu 1 and mu 4 are not adjacent. So, this can't enter. Now, if you enter mu 3, so by minimum ratio it is 9 by 8 and it is 1 by 1, that is 1. So, minimum is here. So, this will leave, now it can enter because mu 1 is leaving. So, now mu 3 can enter, okay. So, the same procedure we will apply in the entire algorithm. So, we got the optimal solution as this. Now, one thing to be noted that it is not necessary that in the optimal solution all these entries for separable programming problems are either greater than or equal to 0, because they have an additional condition also that at most 2 lambdas or 2 muj's are greater than 0 and they must be adjacent. So, it may be possible that all this zj minus cj's may not be greater than or equal to 0, okay. So, this is the optimal solution which we can easily obtain. Now, some problems which appears not to be separable, but they can be separable, they can make separable. How? Let us see. We have the first problem, it is minimizing of this function. Function is you can easily see that function is separable, because you can make f1 x1 as, in the first problem you can make f1 x1 as x1 square, okay, f2 x2 as x2 square minus 4 x2, and f3 x3 as minus 2 x3. So, it will be, it is the sum of 3 functions f1 x1 plus f2 x2 plus f3 x3. The first constraint is also separable, you can easily see it is x1 plus x2 plus x3 less than or equal to 2. So, g1 x1 is x1, g2 x2 is x2, g3 x3 is x3. The next constraint, it is not separable, because it involves product of x1 and x2, it is not separable. Okay. Now, it can make separable. How? Let us see. This can be written as, now this quantity because x2 is greater than or equal to 0, so x2 plus 1 will be greater than or equal to 1. Okay. So, this will be greater than or equals to 2 upon x2 plus 1. This quantity can never be 0, because it is greater than or equal to 1, because x2 is greater than or equal to 0. So, we can take it in a denominator and it will not change the sign. So, this implies x1 minus 2 upon x2 plus 1 less greater than or equal to 0, or x1 minus x1 plus 2 upon x2 plus 1 less than or equal to 0. So, now it becomes separable. Now, it is something h1 x1 and it is s2 x2. Now, it is separable, which is otherwise not appearing as a separable programming problem. So, some problems we have to make it separable, we can make it separable and then apply the technique to solve it. Now, suppose the next problem x1, the next problem. Now, how can we make it separable? The objective function is maximizing f is equals to x1 x2 square and x3 cube. The constraint is obviously separable, it is a linear constraint, it is obviously separable, and other is a non-negativity restriction. Only thing is this objective function is not separable. So, how to make separable? So, you take log both the sides. So, log of f will be nothing but log of x1 plus 2 log x2 plus 3 log x3, which is not separable. Maximizing f is same as maximizing of log of f. Okay. So, you can simply maximize this function, okay, which is same as maximizing log of f. So, now it is separable, it is f1 x1, it is f2 x2 and it is f3 x3. Now, x1 x2 x3 can't be 0, because if it is 0, so maximum will be 0. Okay. Maximum can't be 0, because x1 plus x2 less than or equal to 12, this constraint is there. Okay. So, maximum can't be 0. Okay. So, that is why log of this is defined, okay, because variables are strictly greater than 0, as we have already seen by the feasibility condition. So, in this way we can solve separable programming problems, and we have already also seen that there are some problems which are not separable, but can be made separable. So, thank you very much.